Assalamu alaikum. I am Vivian Shwaikani. I'll be explaining you the last part, which is part 4 of chapter 4, chemical equilibrium. The objectives of this part are to determine whether a system is at equilibrium or not by comparing Q to Kc, and to determine the degree of conversion of a substance at equilibrium. Let's start by the first objective, which is about the reaction quotient Q and equilibrium constant Kc. We know that in a reversible reaction at T0 or at any time T that is before equilibrium, the rate of both chemical reactions, the forward and backward reactions, are not equal. This is how, look here for example, the reactants will give the product in a forward reaction where the arrow is written in a bigger size than the one of the backward reaction to indicate that the forward reaction is faster. Or, in the other way around, here the size of the backward reaction arrow is bigger. This is what to indicate that the backward reaction is faster. At any time before equilibrium, the concentration of the product over the concentration of the reactant is not equal to Kc. Pay attention here that we are considering an example where the coefficient, the stoichiometric coefficient are 1, and this is why here we didn't write anything here exponent because we considered that it's equal to 1, as I said. So as I said, at any time before equilibrium, the ratio of the concentration of a product over the reactant is not equal to Kc, since equilibrium is not reached yet. This is why scientists use the term Q, which is the reaction quotient, instead of Kc, where Q is equal to the same relation as that of Kc. Now, if Q is equal to Kc, the system is at equilibrium. If Q is smaller than Kc, then the reaction system will move in a way to increase Q in order to reach equilibrium. So how to increase Q for Q to be equal to Kc? Look at Q relation. Q is equal to the concentration of the product over that of the reactant. So for Q to increase, the concentration of the product has to increase, because in a fraction the numerator has to increase for the whole fraction to increase, and the denominator has to decrease. So in which direction will the reaction move in order for Q to increase? Actually, it would be in the forward reaction. So the forward reaction will be faster, so more product will be formed, and then Q will increase to become equal to Kc. Now, if Q is greater than Kc, in the same logic, following the same logic, we have to, or the reaction has to move in the direction to decrease Q to reach equilibrium. How to decrease Q? We will decrease it by decreasing the amount of product and increasing the amount of reactant. So this will occur when the chemical reaction moves in the backward direction in a faster way. Now, what is the significance of Kc values? From the value of Kc, we can deduce the species that exist at equilibrium with higher quantities. How? You have to keep in mind that Kc has this form, concentration of a product over that of reactant. Now, if Kc is much greater than 1, again, look at this fraction. It means the numerator here, which is the concentration of a product, is much higher than that of the reactant. We say that the product predominates. It means it exists in high quantity at equilibrium. So although we are at equilibrium, but the quantity of the product is higher than that of the reactant. Now, if Kc is much smaller than 1, the reactant predominates. Why? Because again, Kc having this relation. If Kc is much greater than 1, it means for a fraction the denominator is greater than the numerator, so the quantities of reactants are greater than of the product at equilibrium. Let's do this application 1. Now I will not ask you to pause this application because I want to explain it to you. We have the following reversible reaction, and pay attention that all reactants and the products are found in the gaseous phase. So this is the case of homogeneous equilibrium. At time t0, 1 mole CH4, 1 mole CS2, 2 mole H2S, and 2 mole H2. So we have the number of mole initial. They are mixed in a 250 milliliter vessel at a given temperature. At this temperature, Kc is given to be equal to 0.036. Question 1. Is the system at equilibrium? If not, in which direction will the reaction go? Let's find first of all the concentration of each reactant and the product at equilibrium to be able to answer this question. These are the initial concentration. The initial concentration is equal to the number of mole that is given here, 1 and 1 for CH4 and CS2, over the volume of the vessel or of the container, that is equal to 250 milliliter. It becomes in liters 0.25 liter. Remember that for gases mixed together in one container, we will consider that each gas occupies the volume of the whole container, as if each gas is present alone, and this we have explained it. This idea has been explained in the previous video. Now for the other species here, about H2S and H2, their initial concentrations are the following. Now, what is Q? Q has this, would be written in the same way as Kc. So as you noticed, here is H2, that is the product, exponent 4, and this is for CS2 divided by CH4 concentration at equilibrium and H2S multiplied by 2. Now, what are the values here? The values are 4 times 8, as you can see, multiplied by 4. It is the following. So we will get the following value of Q. By a simple comparison with Kc that is given here and Q, we can directly say that the system is not at equilibrium. But in which direction will the reaction go in order to reach equilibrium? As we explained previously, Q is greater than Kc. So the reaction here will move in a way to decrease the value of Q. Which value or which direction decreases the value of Q? When the concentration of the product decreases. So when we moved in the backward direction. So the reaction is moved in backward direction, therefore reactant increase and the product decrease their concentration. This is question 1. The same application is written again here in order to have all the numerical values in front of you. Now, what is the second question? If the concentration of CH4 is equal to 5.56 mole liter minus 1 at equilibrium, what are the concentration of the other substances? Here, let's refer to an ICE table. Here is the equilibrium or the reactional system. The initial concentrations are the one calculated in the previous slide. Now pay attention to something very important. Why did we write the change here plus, although CH4 is written at the beginning and H2S? Because in part 1 we said that the reaction will go in the backward direction. So actually these are considered to be the reactant and these are the product, because this is the direction. Direction 2 is the direction followed by the reaction. Now you have another way to represent it. You can from the beginning represent the reaction as CS2 plus 4H2 give us CH4 and 2H2S by using these two arrows. But we preferred to keep the same writing, but since the reaction is moving now in the backward direction, this is why those will be considered as if they are a product, their quantities are increased, and this is why we put here what? Plus, since reaction is moving in backward direction. Now at equilibrium, you know, this is would be 4 minus plus the change, here 8 plus the change, and here minus the change. Again, this is the given. This is the table that is photocopied here. Now, solving X at equilibrium, we can solve it from the concentration of CH4 that is given at equilibrium. Look at CH4 at equilibrium, its quantity is equal to 4 plus X. So 4 plus X is equal to this numerical value, and thus X will be deduced to be equal to 1.56. Now the concentration of the other species will be simply get by by applying this. So x8 plus 2x, the x that is found here is its value, and this is the concentration of H2S at equilibrium. In the same way, we can find that of CS2, and in the same way, that of H2. The last idea in this lesson, it's the degree of conversion alpha or degree of dissociation. What is this? To understand what is alpha, consider the following reaction. A will give us by irreversible reaction to B. Again, it's homogeneous equilibrium, so we have to consider the reactant and the product at time. The reaction started, suppose, with N mole of A, and X is the amount of A molecules that dissociated or that is converted, as in the following table. This is A, this is 2B. You know that initially we suppose that we have N0 for A, 0 for B. That change will be minus X plus 2X, you know, while Y. And at equilibrium, the quantities of A in terms of number of mole will be N0 minus X, and for B, it is 2X. What is the degree of conversion alpha? The degree of conversion of a chemical species is the number of moles of this species that has reacted out of 1 mole of it. It means, again, this is the same table of the previous slide, and this is the definition of alpha. Now, to get alpha, it's simply the number of mole of the species that we considered here, A, that is dissociated or converted, over number of mole of A initial. How? To get alpha, we can use a cross multiplication. You can't use this method in exams or in quizzes or something. But this is the simplest idea to explain you how did we get the formula of alpha. Look, initially we had N0 mole of A. This is the number of mole given of A. Out of N0, how much has been converted or reacted? Actually, it's X. It means X has been converted out of N0. Now, according to the definition of alpha, it is the degree of conversion of the chemical species. It is what? The number of mole of this species that has reacted out of how much? Of 1 mole. So here we have N0 of this species. So out of 1 mole of this species, what would be the conversion? It would be alpha. So applying a cross multiplication, alpha of A will be X times 1 divided by N0. We eliminate 1 because it is nonsense here. So alpha will be equal to X over N0. What is X? Look at this formula. It is the dissociation molecules of A, or the dissociated molecule. This is why alpha of A will be equal X over N0. And you can memorize this by heart, but personally I prefer to explain it to you in order to understand where did you get alpha from. And this implies that alpha is less than 1. Now, what about the degree of conversion and the ICE table? Because sometimes they ask us to consider it or to apply it in a table. Knowing that alpha of A equal X and 0 as shown previously, then X will be equal to alpha times N0. Look at this ICE table. Initially we have N0 of A, 0B. The change is what? The change is minus X here as in the previous slide. Now X will be replaced by alpha N0 drawn out from this formula. So instead of X, we will write simply minus alpha N0 and here plus 2 alpha N0. At equilibrium, it will be N0 minus X. It means N0 minus alpha N0, and we will take N0 as a common factor, and this will be the number of mole of B at equilibrium. Alpha actually gives us an idea about the amount of reactants dissociated or converted. It means if alpha is equal, for example, 0.3, this means that 30% of the reactants are converted or dissociated and 70% are not. They stay in the reactional system. Again, I will give you this application, but I will not solve it. I will ask you to pause it, to pause the video, and to do it alone, and those will be the answer. This is for part 1. Again, do part 2 on a scratch paper, and this is the answer of part 2. Now for part 3, again, pause the video, do part 3 that is here represented in red, and this is its solution, compare it to your answer. And finally, for number 4, if the temperature becomes T equal to 150 degrees Celsius, it means it differs from the initial temperature at which the exercises is given. Does the value of Kc stay the same? Justify. We know that Kc changes since the temperature changes, and we noticed that Kc depends only on temperature. Now I will ask you to pause again the video and to write what do you have in the agenda, and I will see you maybe in the next lesson. Thanks for your watching.